Welcome everybody to today's webinar, welcoming speakers of the IEA PVPS Task 16. Let's wait for a few more minutes until we can get started so we have everybody on board. So please hold the line. Welcome everybody. This is ISIS with today's webinar on the IEA PVPS Task 16 work on all-sky imagers benchmarking. Please hold the line and we will begin shortly. All right, let's get started. Welcome everybody to today's webinar by ISIS, the International Solar Energy Society. We are going to hear a webinar on IEA PVPS Task 16 on the topic of all-sky imagers benchmarking. And it's my pleasure to welcome you, the audience, and our speakers to the webinar. My name is Arabella. I am the Congress's Communications and Outreach Officer here at the ISIS HQ in Freiburg in Germany. And I will give you a short introduction into ISIS and the work we do, as we have many new participants joining us on the webinar today. So ISIS, who are we? ISIS is a UN-accredited membership NGO founded in 1954 and accredited since 1992. ISIS represents a diverse membership of academics, researchers, energy practitioners, consultants, students, businesses, and advocates from countries from all around the world. And our vision is 100% renewable energy for all, used efficiently and wisely. Here at ISIS, we have a broad range of key activities to foster this mission. For example, we hold biannual congresses all around the world. One is the ISIS Solar World Congress, and we've got one coming up next year, and as well as the Eurosun, which is coming up in 2 years' time, which is now jointly organized with the IEA SHC program. We also have two key publications. One is a very well-known and long-established journal, that's Solar Energy, which we actually started back in the 50s. And then just now in 2021, we added to it Solar Energy Advances, which is our fully open access journal. We also have webinars, obviously, as the one we have today. And we have education initiatives, both online and offline, when we are on site for our conferences. And additionally, we share relevant solar information by means of infographics, as well as our Solar Energy Museum. That's an online museum going back all the way throughout solar history. Before we get started with the webinar, I want to have a quick word on the Q&A session. The Q&A session is going to be a cumulative Q&A session at the very end. So we're going to hear all presentations first, and then we have a joint Q&A session. You can type in your questions anytime throughout the webinar, and you have a chat box on your GoToWebinar panel to do so. If you send in a question, please keep the question short and precise, and also indicate who the question is for, so that our moderator can then assign the questions. And on the topic of moderator, it is my great pleasure to introduce you to our moderator of today, which is Dave Renee. Dave served as the president of ISIS from 2010 to 2019, and he now holds the position of ISIS immediate past president. From 1991 until 2012, Dave managed the solar resource assessment activities at NREL in the US, and in 2012, he then formed his own consultancy, Dave Renee Renewables. Dave is quite dedicated, I have to say, to the concept of renewable energy, and he's been with ISIS for many, many years, and it's my pleasure to hand over to Dave now. Thank you, Dave.
Well, thank you very much, Arabella, for your kind introduction, and I'm very pleased today to moderate this webinar on a very important technology that's been under investigation for a number of years and is becoming now a commercially viable technology for providing nowcasting and short-term forecasting information in the operation of large-scale photovoltaic systems for utility operations. And I'm very pleased to introduce our first speaker, who happens to be the task leader of this work that's underway under the International Energy Agency's Photovoltaic Power Systems Task 16 program. The task leader is Jan Riemann, and he will be giving us an introduction about Task 16 as well as the technology we're going to be talking about today. Jan has a background of geography and climatology, and for more than 20 years has worked at SME Meteotest in Bern, Switzerland. He's a project lead of the Global Solar Radiation Database Meteonorm, which most of you are very familiar with, and he's also, as I said, the task leader or operating agent, as the term used to be called, of the IEA PVPS Task 16. He's been leading this task since 2017. So I'm very pleased to turn the podium over to you, Jan.
Yes, thank you very much, Dave, also for your kind introduction. Now I'm trying to share my screen. Okay, can you see it now?
Yep, all good.
Okay, thank you very much. Yes, I will give just a short introduction about the framework of the work where the benchmark has been done. And this work has been done in our task 16 of IEA PVPS. Okay, the background itself, IEA is part of the OECD, and IEA has such called TCP's Technology Collaboration Program, where PVPS is one of them. It exists since 1993. And our task 16 exists since 2017, and before it has been a task of the SHC program. We are about members of 19 countries, mainly universities, research organizations like NREL, Met Service, and service providers are part of it. It's not totally global, but it's quite a big share of the world we have participants from. Why a solar task? So the solar resources are the fuel of PV, CSP, and solar thermal energy. Those three groups we are still working for. However, the main activity is linked to PVPS, to power PV. Big PV and high penetration need high quality for meteorological information. And our task gives added values like independent benchmarks, like the one we are presenting today. We are making state-of-the-art descriptions, mainly with our solar resource handbook. And finally, we try to lower the uncertainties of the forecast as well also of the solar resource data, which lowers then the cost of implementation and which makes possible to deliver to have more PV. Currently, we are in our second phase of our program, which ends next year, and we are planning to have 3 another years, which will be ongoing till June 2026. The task is organized in 4 subtasks. The first one is dealing with measurements and models. The second one about enhanced data and bankable products. The third one about solar resource solar forecasting techniques. And the all sky images we are talking about is part of this subtask number 3. Subtask 4 is about dissemination, and we are doing webinars like the one today, but also giving workshops at conferences. And as I said before, we are updating our solar resource handbook together with NREL every 3 to 4 years. Currently, we are working on 5 reports. Just to give you also an image of what we are doing aside the benchmarking of ASIs, we are producing reports about benchmarks of solar resource data, a benchmark of GHI, global horizontal irradiance gap filling methods is ongoing and will be published soon. Then we have been doing a benchmark of probabilistic forecasting. The report will be done until next June. We have written a report about firm power production, and the start of the 4th edition of the solar resource handbook has been started. It will be available in about 1 year. As said before, our main product is this handbook. but also we have some online archives, code archives, and also links to measurement networks. Just one slide about ASI. It is based on the cloud motion forecast based on this all sky images. This is the optimal method for the minute, time, and 100-meter spatial scales. You see this graph to the right. The optimal method depends on the temporal and spatial scale. For example, if you want to have a forecast for the next day, it's the best to have a numerical weather prediction model. But if you are focused to minutes and, as I said, to 100-meter scales, then ASI forecasts are optimal. For which type for what can they be used? For example, they minimize cost and risk for power plants, for grid operators, for improved situational awareness. And mainly it is due to that the cloud passing are the largest influence factor for short-term fluctuations of irradiance on local scales. Okay, that's all from my side to give a background information for the ongoing next presentations about the benchmark.
Okay, Jan, thank you very much for that excellent overview of task 16 and of the important topic of today's webinar. So our first speaker will give a very comprehensive overview of work that's been done in the all-sky imager field. He's Stavros Logothetis. He graduated from the Department of Physics at the University of Patras in 2017 and received his master's degree there in applied meteorology and environmental physics in 2019. And since then, he's a PhD candidate at the Laboratory of Atmospheric Physics, with his main research activities focusing on solar radiation transfer in the atmosphere and investigation in the effect of aerosols and clouds and solar resource and nowcasting. Excuse me. So Stavros, I'll turn the floor over to you.
Hello, thank you. Thank you for your nice introduction. Can you see my screen?
Yep, all good.
All good? Okay. Okay. The title of my presentation today is Solar Irradiance and RAB Events Forecasting based on all-sky imagers. And this study was conducted under the framework of the International Energy Agency PVPS Task 16. And we participated in subtask 3, where the overarching goal was the evaluation of the current and emerging solar forecasting techniques. Our task was to investigate and qualify the current state of the art of solar nowcasting techniques based on all-sky imagers. The first paper of our study was written to interpret the results from a benchmark exercise focusing on the solar irradiance nowcast performance derived from the all-sky imagers. During the analysis of the first paper, we noticed that those nowcasts are able to detect the sudden changes in solar irradiance. And this was the reason why we decided to take our research one step further and to investigate the applicability of using such kind of systems to detect solar irradiance RAB events. Let me do a brief overview of the benchmark campaign. It took place at CIEMATS experimental site in Almería from August to November 2019. And from the 3-month observational campaign, 28 days were selected for the validation, while the other days were used for algorithms training. In total, 4 ASI systems were used, which varied in the camera's type. Using these 4 camera setups, 5 different nowcasting methods were applied, varying on the underlying cloud segmentation and forecast algorithms. In addition, we have also used 2 persistence models for comparison reasons. These 5 different nowcasting systems can be divided into two main categories. The first 2 ASIs, ASI 1 and 2, they apply consecutive step forward physical steps in order to provide their solar nowcasts. while the other three ASIs are mainly depends on deep learning techniques. All methods nowcast the global horizontal irradiance, or GHI, with a time horizon of 20 minutes with 1 minute step. Let's move on the results of our first paper dedicated to solar irradiance forecasting performance. Here we wanted to investigate the ASIS performance under different time horizons and also intervals. In these heat maps, we calculated the mean absolute error on the left and the root mean square error on the right under different lead times and time intervals. In particular, the vertical axis of each graph shows the starting forecast minute, and the horizontal axis shows the number of minutes that included in the error calculations. For example, the black box on the left figure shows that the corresponding metric is calculated using the forecast starting from the 5 minute, including up to 3 minutes ahead, which is the 5, 6, and 7 minutes. It is apparent that higher deviations are documented as lead time increases. Overall, ASI-2 revealed the mean absolute error values that vary from 15 to 45 watt per square meters, which is the highest forecast performance among the ASIs. The lowest errors are observed for 1 minute lead time and time interval, while the opposite behavior is documented for 1 minute time interval and 20-minute lead time. Then we investigated the overall forecast performance of all implemented algorithms under various cloud conditions. As you can see on the right table, the campaign days are classified into 6 main cloud clusters. The cloud-free days are called as Cloud Cluster 1, while the days that include scatter cloudness, including low, multiple, and high or middle clouds, are called as 2L, 2M, and 2H. 3H are the days with cloud-free conditions during the half of the day, and scatter cloudness with high or middle clouds during the other half. Finally, we have the Cloud Cluster 4A, which are overcast cloud conditions during the half of the day and scatter during the other half. The graph on the left shows the different performance of all the implemented algorithms for each cloud cluster, while the table below depicts the algorithms with the best performance. All algorithms provide their highest deviations for scattered cloud conditions and overcast skies. But based on the bar plots, we can see that for all cloud clusters, at least 2 ASIs are superior to persistence algorithms. And particularly, the ASI with the highest appearance is again here the ASI-2. Only under cloud-free conditions, a persistence algorithm was able to outperform all the ASIS forecasts in terms of mean absolute error. Then we investigated the ASIS performance against the persistence under different cloud clusters and also lead times. On each figure, the solid lines represent the ASIS forecast, while the dashed lines correspond to the persistence. Each color corresponds to the different cloud clusters. We can see that on the left, ASI-2 provide better performance than the persistence at each cloud cluster and at each lead time, even under cloud-free conditions. While ASI-3 on the right can outperform the persistence algorithm at distant lead times at all cloud clusters, but at short lead times is not able to superior the persistence. ASI-4 and 5 underperform the persistence algorithm at any lead time for cloud-free conditions, but at cloud clusters 2L, 2M, and 4A, those two ASI systems superior the persistence at all lead times, and in the other cloud clusters only at distant lead times. Before I proceed to the results of the second paper, let me present you a cloud day of the campaign. The figure on the right shows the diurnal variability of solar radiation for a typical 2A cloud cluster day. The figure on the left, the figure on the right shows the algorithm's forecast performance in terms of relative root mean square values, which are calculated including the 20-minute time forecast horizon at each minute of the day. The GHI diurnal variability is dense and sudden, with the reduction reaching to 600 watt per square meter, caused by the presence of heterogeneous clouds. Then, if we zoom in the graph between 9 and 11 o'clock, consecutive changes of GHI are recorded, including time frames with enhancement events. We can see that during these sudden changes on the GHI, ASIs often show better performance than the persistence. So, considering the quite good performance of ASIs nowcast under strong GHI fluctuation, was the reason to further investigate the feasibility of using those systems to predict solar irradiance RAB events. There is more than one definition of solar irradiance RAB events, and particularly the definition depends on the application. Here, we aim to consider as a RAB event as any case where transient clouds cause sudden changes in the incoming solar irradiance, including both enhancement and reduction events. The flowchart on the left shows step by step the applied methodology. The RAM events are detected through the calculation of the RAM rate for the normalized GHI. The RAM rates are calculated both for the reference measurements and also for all algorithms forecasts. The threshold limit that separates the RAM from the no-RAM event is calculated based on clear sky RAM rates, which are calculated using only ground-based measurements. Then, the threshold limit at each time horizon is defined as the 99th percentile of the clear sky RAM rates. Then, if the algorithm's absolute RAM rate value exceeds this corresponding predefined threshold, then a RAB event is documented. On the right, I give you an example of how we calculated the threshold that separates the RAM, which is the area with the green color, from the no RAM, which is the area with the red color, at a 10-minute forecast time horizon. Now, it is worth mentioning that our methodology can be adjusted appropriately depending on the application. For example, if you want to detect only dense RAMs, an increased predefined threshold is mandatory. Before I proceed to the results, I would like to show you the verification of our approach, and particularly using only observed GHI measurements. The blue solid line here presents the diurnal variability of the GHI measurements, while the black dots indicate the absolute RAM rates at 1 minute time horizon. While the horizontal red line show the predefined calculated threshold limit. If we zoom into two different time frames, we can see that our proposed methodology is suitable either to identify the sudden solar irradiance fluctuation or to detect the no RAB event cases. Before I move on to the results, I would like to show you how we did the statistical analysis of our work, and the table on the left shows the confusion matrix for all possible forecasted cases. The diagonal elements of the confusion matrix represent the correctly detected RAB or no RAB events, while the off-diagonal element shows the false predictions for the presence or the absence of a RAB event. Our methodology is applied at two different temporal analyses. Firstly, we have detected the RAB events at each specific time horizon of the algorithms. Secondly, we have detected the RAB events over the whole 20-minute time horizon. For the 20-minute window analysis, that we also called it as a time window analysis, at least one true RAB event is required by the ASIs to define a true RAB event, not restricted at the same time horizon with the reference measurements. In addition, if no RAB event is detected, both from the reference and the forecast of the whole 20-minute window, then a true no RAB event is recorded. On the contrary, a false no RAB event is denoted if the ASI nowcast failed to predict any RAB event within the 20-minute window, while there is a RAB according to the measurements. Finally, our results are qualitatively presented in terms of total accuracy, which show us the overall prediction of the true RAB and no RAB events. Now, let's move on to the results section, and in this graph, we can see the changes of the possible cases in the confusion matrix at each time horizon and for the entire 20-minute time window. In order to further support the significance of our work, I decided to show you the results from the persistence first. we can see that the persistence can't predict any RAB event at any time horizon, so we concluded that it can't be used in studies of RAB event detection. On the other hand, ASIs revealed that they are able to detect ramps to a certain extent, and particularly on the left, ASI2 can capture the true RAB event cases up to 65%, while they have the tendency to wrongly predict no RAB event cases. ASI2 can capture correctly the no RAB events up to 95%. Oops, sorry. I would like to mention here that ASIs 1 and 2 are initially developed to provide spatial solar irradiance forecasts and have been delimited only to a small area for the purposes of this benchmark, resulting to lower true RAB event performance. On the right, ASI 3 can capture the true RAB event cases up to 90%, while this system have the tendency to wrongly predict RAM cases. For both systems, the percentages of true detected cases decrease as the time horizon increases. ASI 4 and 5 provide similar results and patterns with ASI 3, and particularly they can capture the true RAB event cases up to 90% and the true RAB event cases up to 85%. Both reveal the tendency to predict wrongly false RAB event cases. So let me summarize the results for our first from our first paper. What we saw is that ASIs within the whole validation period, ASIs 1 and 2 reported the lowest deviations among the ASIs, and that in general among the ASIs, the ASIs deviations follow an increasing trend as the time horizon increases. Again, with ASI 1 and 2 providing the highest performance, either at low or at distant lead times. When we divided our work in different cloud clusters, we saw that ASI 1 and 2 can outperform the persistence models at all cloud clusters and lead times, and for the time horizons that are longer than 5 minutes. And the other three ASIs are also efficient to beat the persistence models under cloudy skies. Under the cloud-free conditions, only 3, and particularly ASIs 1 to 3, proved to be capable of providing better results than the persistence. And the overall conclusions of our first paper was that specific ASIs outperformed the persistence models even under clear, scatter, and overcast skies. The summary of our second paper is that the performance of all detected RAB event cases was clearly connected to the applied forecast algorithms, and we saw that the true predicted RAB events decrease as the time horizon increases for all ASIs. The ASI 1 and 2 have a tendency to wrongly record no RAB event cases, which happens more often than ASI 3 to 5 systems. And on the contrary, ASI 3 to 5 have the tendency to wrongly predict the RAB events, which happens less often than ASI 1 and 2. And all ASIs together can predict RAB events accurately from 30 to 95% of the cases. And the overall conclusion, and this is how I like to close my presentation, is that the selection of the most suitable ASI system in order to provide solar irradiance RAB events forecasting depends on the application. Thank you for your attention, and feel free to check our recently published paper online, and also to ask any question in the chat box.
Thank you, Stavros, for this very comprehensive and interesting overview of the work that you've been doing with all-sky cameras, all-sky imagers. I think especially of interest is the ability to predict ramp events, which of course is a very key issue for utility operation of grid-scale PV systems. Our next speaker, and let me just remind all the attendees here that please submit your questions to the speakers in the questions box of your app. and we'll have a Q&A session after all the speakers have completed their talks. So next we have Bijan Nouri. He received his PhD in mechanical engineering from RWTH Aachen University in Germany. And since 2011, he's been working for DLR in Almería, Spain, where his research focuses on thermal qualification of concentrated solar thermal power plants, solar irradiance nowcasting, and solar power plant modeling. So Bijan, I'll turn the floor over to you.
Hello, thank you. You see my screen?
Yep, all good.
Okay. Okay, so, oh, that didn't work. Okay. Okay, so this presentation is titled All Sky Imager-Based Irradiance Nowcasts, Combining a Physical and a Deep Learning Model. And as you can see, there are quite a lot of people involved in this work, but I would like to point out Mr. Jan Fabel because he was the main driver behind our deep learning model, which is our most recent adaptation of our work. Okay, so then let's start. So here you can see the agenda of this presentation. And basically what I would like to present to you is our work since the benchmark. As we have learned quite a lot during the benchmark, so we found quite a lot about the weaknesses and strengths of our approach, and we also got an idea how to improve our approach, which strategies could be helpful to improve the approach. For that, I will present to you two distinct nowcasting approaches based on the ASIs, a physical-based approach as well as a machine learning-based approach. And our final nowcasting system will then combine these two to a hybrid system. Furthermore, I will present to you the validation results of our improved system compared to the benchmark status. I'm not going to go so much into detail like Stavros. I'm just giving you like an overview or an overall results of the skill score and also of the ramp rates, but not so much into the details. And for the ramp rates, I use exactly the same definitions as presented by Stavros. So I will not go again over the definition of them. And then there will be also a conclusion. So let's start then. So our starting point is our physical nowcasting approach. Here we have a chain of processing steps, and this starts with the cloud detection, which can be seen here on the left-hand side. So we have the sky images, and we have to identify now which part of the sky is cloudy and which part of the sky is not cloudy. For that, we use a convolutional neural network. Then the next processing step would be the geolocation. For that, we need at least 2 cameras. More cameras are beneficial, but 2 are already sufficient. And with that processing step, we identify the cloud height. And in addition to the cloud mask, which are provided by the cloud detection, we can then really geolocate the clouds in a 3D space. Then we also want to know where the clouds are heading to. So we have to track them. We evaluate for that a sequence of raw images, and we actually evaluate a sequence of differential raw images and difference raw images. And in the end, we apply a cross-correlation algorithm and identify for every single cloud in the sky a motion vector. The next processing step would be shadow projection. So we have our 3D cloud model, we need a topographical map, and then we have a ray tracing algorithm, and we identify which part of this topographical map will be shaded and which part will be sunny. However, we want to convert this into an irradiance map, so we have to analyze also the radiative effect of the clouds. For that, we use a probabilistic approach, which evaluates current and historical transmittance, cloud transmittance, as well as cloud height measurements. And we can combine all these processing steps, and we create in the end such a 3D cloud model, which can be seen here in the center. There are also some red arrows, quite small, which show the general motion direction. And then we have here also our topographical map, and this is a quite large map, so it has a coverage of around 64 square kilometers. And the red dots in the center are the positions of the 2 cameras which were used to generate this map. And the color coding is the GHI, but this could also be the DNI, for example. And we create such maps for the current conditions all the way up to 20 minutes into the future ahead. And that would be our physical model. However, during the benchmark, we already used the adaptation of this physical model. We combined it with a persistence model. And this is a smart persistence model, which takes into account a change of the sun position in the sky. And we combined these two models via accuracy weighting approach. For that, we had to conduct a real-time validation. So this is conducted all the time during the operation of the nowcasting system. And we consider the irradiance maps which describe lead time 0, so the current observation, as reference. And we compare this reference information with previous nowcasts which describe the same timestamp. So for example, the lead time 10 from 10 minutes ago would be compared to the current observation. And we can calculate then an RMSE if we look at larger time windows. So for example, we use normally 5 minutes, and we can calculate the RMSE for each model and for each lead time. And when we have the RMSE for each model and each lead time, we can use this weighting algorithm, which you can see, this is the second function. And we combine them we combine both models according to the current performance of these models during the real-time validation. The advantage of this approach is that the weights are adapted for every single timestamp and every single lead time. So we will see this directly if the conditions change, if the performance of one of the models will increase or decrease. The general idea of this approach is that the hybrid approaches exploits clear divisions in strengths between fundamentally distinct models for distinct prevailing conditions, and it will outperform each model by itself. And as this worked quite well, we decided to introduce a third model. And this is then a machine learning model, and in the end, an end-to-end machine learning model. And so basically what we see here without the machine learning model, this was basically the final model presented by Stavros. And this will be now our improvement. And I will talk a little bit about the machine learning model. So what do I mean with end-to-end model? So here you can see again all the processing steps used by the physical model, and we basically forget about them. We don't use them. We have our input, the sky images and the time series. We do some feature extraction. We have our deep learning model, and then there should be a irradiance nowcast. And how did we do it? So our machine learning model is already a combination of different models as we have different kinds of data inputs. So it is a multimodal deep learning model. And we are using sequential data, so sequences of all sky images as well as time series data. Therefore, we decided to use a transformer model, as transformer models are more or less recent developments which showed high performance for sequential data, similar to recurrent neural networks, but the recent publication, it showed that the transformer models might outperform them. And this is also what we have seen in our internal benchmark, that the transformer models did outperform actually the RNNs. And we use a vision transformer for the all sky imager sequences, and we work with 5-minute sequences. And we use a time series transformer for the time series data. Here we use a time window of 30 minutes, and as input, we have DNI, GHI, and DHI measurements, as well as the solar position. Both models will create a feature vector with the same dimensions, and then we have to combine everything, and for that we use a multi-layer perceptron. And this is actually quite simple MLP. I believe we used only a single hidden layer. And then this MLP will create a multi-step future irradiance nowcast, and this will be again GHI or DNI depending on the application, and horizon up to 20 minutes into the future. The good thing about this model is we can train it at once, so we don't have to train first the vision transformer, then the time series transformer, and then the MLP. We train this whole package at once, and for that we used a training data set of around 400,000 data points. These are basically timestamps within the time window from 2016 to 2019. We did not use the entire data set in this time window, only partial points, as this is PSA data, and around 70% of the data would be clear sky, which is not that interesting. But still, we had 400,000 interesting data points. Okay, so much about the multimodal deep learning model. So this is then the third part which was used in our new hybrid model. So we have our physical model, the persistence model, and this multimodal model. Now let's look into the validation results. We used again the same 28 days as presented already by Stavros, and which are also described in his publications quite in detail. However, I'm not going to go so much into the details of the validation, so this is really just a rough result, so the overall performance of the system. So for example, we do not discretize the data here. So these are the RMSE curves, for example, over the entire 28 days. So we have the RMSE on the y-axis for GHI and the lead time on the x-axis. And we have three curves. The blue one is the persistence, so just the persistence as reference. The purple curve is basically the hybrid system as used during the benchmark, so the physical plus persistence. And the green curve is our new system, so the physical plus persistence plus the multimodal model. And we can see that both hybrid approaches are outperforming clearly the persistence, but we can also see that the new hybrid model is outperforming clearly the old one. And especially if you look into the skill score, then yeah, well, it was already clear from the left-hand side, but here we see it clearer that we have a positive skill score. And if you look into the average skill score over all lead times, then we see that in the previous model, we achieved the average skill score over all lead times of 12.6% with a standard deviation of 5.5% over the lead times and the maximum of around 19% for lead time 11. And with the new hybrid model, we increase this average skill score to 24.9% and the standard deviation of 4.5% and a maximum, again, at lead time 11, around 30%. So this is really a huge leap forward in terms of skill score, so more than an improvement by more than 12% points, actually. So it looks like that this hybrid approach has potential. But now let's also have a look into the ramp rate validation. So again, we used exactly the same validation method as presented already by Stavros. And we looked here into a time horizon range from 1 to 20 minutes, which is also described quite well in his paper. And here are the results. So on the left-hand side, this is the model as used during the benchmark. And on the right-hand side, this is our new model. And the first thing which we see is the overall increase in accuracy. So we have an increase from 78 to 80, almost 82%. Furthermore, we see that we have the biggest change in true positive ramps. So we increase from 67 to 75.6%, so more than 8% points up. At the same time, we also see more false positive ramps. So we did find more existing ramps, but we also saw a little bit more ramps which do not exist. But overall, we have an improvement. So that's already a nice thing. However, as I already mentioned, we create irradiance maps, and this evaluation only takes into consideration a single point in space. And we would actually throw away quite a lot of information which is provided by our system, and we should exploit it. So we also evaluated what happens if we look a little bit more around this one single point in space. As I said, our irradiance map have a coverage larger than 60 square kilometer, but we only evaluated an area of 1 square kilometer around the point forecast. And then we can see that the overall accuracy, so again, on the left-hand side, this is the benchmark system, on the right-hand side, the new system. And the overall accuracy increases for both systems by a little bit more than 1% point. But we see for the true positive ramps an increasement by 5% points for both systems. But for both systems, we also see an increase in false positive ramps of 3%. But overall, if you look at the bottom right, so this would be now the 1 square kilometer with the new model, we have an overall accuracy of 83%, which is then an improvement by around 5% compared to the benchmark and the single point. So also here, I would say that the new model is not just, let's say, optimized on RMSE. It also has really an impact on the ramp rates as defined in the work from Stavros. So now we can conclude. So possible improvements of the ASI system have been identified during the benchmark. And what we have seen is that the hybrid approach based on the real-time validation has quite a lot of potential, and we could enhance it by introducing additional model, an additional really fundamentally distinct model it has to be. And we decided to use this end-to-end multimodal deep learning model, so this combined vision transformer and time series transformer. And we have seen that the overall skill score improved by more than 12% points, and this is really a huge leap forward, I think. But we also have seen that the ramp rate predictions were better, so we increased this by around 8% points. And if we look also into the space, then then we are talking about 13% points improvement, and the overall accuracy would also increase by over 3% or 5%, depending on which system we take into account. And so our main fazit is that the hybridization approach exploits strengths of fundamentally distinct models, and this really appears to have merit. Here you can see the corresponding publications which are cited in this presentation, as well as some funding information, which at least our funding information for this work. Thank you.
Thank you very much, Bijan. Really interesting results there, in both in improving the accuracy of the nowcasting methodologies, but especially also the further improvements in ramp rates, which are certainly of big concern to utility operations. Next, we have as our speaker Andreas Kazantsidis. He is the director of the Atmospheric Physics Laboratory and a professor at the Physics Department at the University Patras in Greece. Andreas has been focusing on his research on transfer of solar radiation in the atmosphere and on the effect of various atmospheric parameters such as clouds and air particles, and is with particular emphasis on solar resource and forecasting with extensive use of radiated transfer models in synergy with ground-based imagers and measurements, as well as satellite estimations. Andreas is a co-leader of the main activity on this work and on all sky cameras, and has been involved with Task 16 for many years, including the Task 16 predecessor, Task 46, that was the solar heating and cooling program at IEA. So Andreas, I'll turn the floor over to you.
Thank you so much, Rene. Can you see my screen in full mode, maybe? Here?
Yes, all fine. Go ahead, please.
Yes, thank you so much. After all these presentations, I will give you a short overview about the current status based on the results of our benchmarking exercise, as well as some future perspectives, some future thoughts for all sky images and solar nowcasting. So some take-home message from benchmarking exercise. It was the first time actually that we tried to place next to each other different prototypes or semi-prototypes of all sky images and try to make some comparisons. This was the idea that we had some years ago in the frame of Task 16. We performed a so-called blind campaign with different hardware, different software modules, and tried to find the weaknesses as well as the advantages. What is coming through for sure is that the outcomes of this campaign have been proved to be beneficial to all participating groups. Nowadays, new algorithms, better approaches are developed from all groups based on the outcome of this benchmarking exercise. An example is this presentation from Bijan, but also the other groups have made a lot of progress during the last recent time. We would like to investigate deeper and compare not only solar radiation outputs from all sky images, but also how they calculate specific parameters affecting the nowcast, like the cloud velocity, the cloud cover, or the aerosols. So this would be beneficial. However, these outputs are not provided in all sky images that participated in the campaign. So we just leave it a little bit aside. And moreover, apart from the results on GHI that you saw before, also DNI forecast should be investigated. But after seeing previous presentation, I would propose to have another campaign, because as you see, there are all sky imaging forecasting is such a hot topic, and more algorithms and new results are coming all the time. However, if we focus on the benchmarking exercise, we realize that the ASI-derived solar irradiance forecast can outperform the traditional persistence model, even under clear scatter and overhead skies. It was a result that was not clear when we started the campaign. There were still doubts for this. All the imagers proved to be efficient under cloud skies. Some of them are able to outperform persistent models at all cloud classes and at all time horizons. Then, as you see, we also made the second paper about the RAB event detection, and we found out that the RAM events are captured with success from 30 to 95%, depending on the all sky imager type. Of course, this performance decreases as the time horizon increases. So, what are the future perspectives for ASI nowcasting, and how it could increase their performance? There are some thoughts. First, you saw it had a campaign that included only visual modules. I think that the combination of visual and inference modules will increase the derived information for clouds. It would go for better estimation for cloud-based heights, cloud types, clouds information close to the sun, which are crucial for nowcasting. Then the combination of high-end and low-cost systems, as well as networks of all sky images, is expected to increase the spatial and temporal information. And this is also important. We are now, I think, in the era of all sky imager networks, and this is very important because such networks could provide valuable information on the detection characterization of clouds, as well as to have observation information of the 3D cloud structure. And this is a valuable input to any model, physical or machine learning, in order to forecast the change of the cloud shape, because nowadays we go by just find the velocity of the clouds and try to use only advection, but we cannot take into account convection of clouds. So for this scope, I would expect that in the near future we will see new, innovative, flexible systems of all sky imagers aside with ancillary meteorological, atmospheric, solar energy measurements, with synergy with physical models, methods of computational vision, which is important, and deep learning. I think that in the next year, this is the way forward. And based on this, we planned the future activities for the extension of Tax 16 in the next 3 years. And you see here the main scopes and our main objectives. First is to integrate the cloud classification in the nowcasting scheme. Then it's try to get measurements of irradiance from all sky imagers and validate them, the results with local pyranometers or other instruments. Also use all sky networks in order to extend our forecast for areas and longer forecast horizons. Use the forecast from all sky imagers in order to improve the energy management system. Compare and combine all sky images with satellite-based forecasting in order to bridge the gap between these two different methods that seem to be now to be fragmented. We are coming in the years of the Meteosat third generation, so prediction based on the third generation of Meteosat, as well as the second generation, with focus on irradiance, on single signs, and on RAMs will be beneficial. And from all this, we expect to develop further the application and of the cameras to come with user-oriented evaluation metrics and determine the added economic value of using all sky images based forecasting. So the most important for the ASI community, if I may say, is to try to transform all sky images to reliable, robust, and high-quality instruments, not just modules, not just commercial cameras, for meteorology, atmospheric sciences, as well as the solar energy sector. And we all hope that this all sky images benchmarking paved the way for this goal. So with this ultimate goal, I would like to thank all the participants in the campaign, many groups. Special thanks to CIEMATS and DLR for hosting us at Plataforma Solar in Almería. Special thanks also to Wilfred van Sark, who is the co-lead in this activity, Elke Lawrence, who coordinates the subtask for solar energy forecasting, and of course Jan for coordinating the whole task. Of course, many thanks to ASIs for hosting us, and to you all.
Okay, thank you very much, Andreas, for that great talk, and also for the future prospects for this technology. I think it's really interesting to, at some point, to get some sense from the utility industry itself, how they perceive the value of this technology, these all-sky imaging technology, and how they can make good use of it. It seems like from the scientific side, we're making significant progress in their utility, and it would be good now to get the response from the utilities and on how they perceive this technology. So now I'd like to move into the Q&A session. Please feel free to submit your questions in the questions box of the app, of the GoToMeetings app. And I'll just go through them as they come in. The first question was addressed to Stavros. Could you tell us which software you use to analyze the measurements of the solar radiation that you presented in your papers?
In what software I did the statistical analysis, maybe, or what software the partners used to apply their systems. I did all the analysis, all the statistical analysis in Python software, but I think that the partners applied their solar irradiance nowcast at different softwares. I think that they worked on also in MATLAB, I think, if I understand well the question, of course. But I did all the analysis in using Python.
Okay, thank you. Also, this one is directed to you as well, Stavros.
Yes.
Thanking you for your presentation. And how do you deal with the camera limitations like pixel saturation and atmospheric logarithmic illuminance in your calculations and your models?
I think that each partner dealt differently on how they extracted the saturation areas from the sun on the images. As far I know, because I didn't apply the algorithms. I just received their final solar irradiance nowcast, and I did the blind comparison between the forecasts. But as far as I know, all of the participants extracted the solar the saturation of the sun, and I think that only the deep learning techniques they used the images as they are, and they didn't. I think only as the 3 they detect the saturation pixels and extract it from the analysis. I think ASI-4 and 5 that they relied only on deep learning techniques. They used the images that captured by the ASIs as they are, in order to provide the solar irradiance nowcast?
Okay.
If I may say a few words,
Yeah.
so to define how this campaign has been formed. Actually, University of Patras took the lead in order to make the analysis of results that will come directly from the partners. If someone can see the papers, he can find for each all-sky imager the relevant literature and the methodology that has been used. But in the frame, to have a blind campaign for all partners, we, as a partner that didn't have our own camera there, took over the analysis of the results. But we just took the radiance and some ancillary data from ground-based measurements, of course.
Yeah, good. Thanks, Andreas, for that additional comment. And would anybody else like to comment on that question, or can I move on to the next one, which is basically addressed to the entire panel here? Do you perceive a time when hemispherical mega PV farms globally can be connected into a super terawatt hyper grid being electrified 24/7 from eternal sunshine? Yes. Referred to by the questioner as a rotating starship planet. So that's a much broader question than the specific topic here, but it's quite an interesting concept that we hear about quite often. Mega PV grids or super grids with mega PV farms providing the input. Would any speaker like to comment or address that question? The whole idea of super grids.
Perhaps we didn't do that, of course, in the ASI benchmark. We do talk about firm PV power in task 16, how to get a firm 24, 365 days power made by my solar energy. And to have a global grid is one solution. The other one, as we are working on, we say with curtailment and with storage, you can reach to this goal also quite easily and cheap.
Yeah, that's a good point, Jan. Thanks for bringing that up. This is an important question, important concept as we consider the prospect of a 100% renewable energy future and super grids, and the role of PV in those grids, of course, is a key component of that. It's not beyond the scope of this particular webinar, but stay tuned. We may have future webinars. We've had some in the past already on firm PV power, and we are, as Jan said, there's work being done in this task, not only in task 16 but elsewhere. So stay tuned. I know ISIS is always looking for webinar topics on this very subject. The next question, let's say I'm going through here and somebody came in late and asked if this webinar is being recorded, and yes it is, and Arabella will give more information about that at the end of the question and answer session. So here's one for Bijan. Which of the nowcasting approaches, either the physical or the hybrid models, is most available or most suitable for practical applications? For example, sizing a PV facade in urban environments.
So we developed the system so that we use both at the same time, and it is real-time capable. So because both systems use exactly the same data set, they run with the same wrap-up software, basically. So you can run both of them in parallel and combine them in parallel. So from that point of view, I would use the hybrid as it has the highest performance. And otherwise, they have more or less the same requirements in terms of data availability, in terms of what kind of data it is. So Yeah, you could use either one of them, but I would use them always in the combination. The combination will always outperform each of the models by itself.
Great, thanks. And this next question is also addressed to you, Bijan. The results of the full hybrid model look great. In my experience, the RMSE as a metric favors DNI, GHI, nowcast, which are more averaged. Combining multiple nowcasts, I expect this to be the case here. Do you have it, or did you have a look at other non-quadratic measures like mean absolute error?
Yeah.
And do you observe the same improvement there?
Yeah, we also looked at the mean absolute error. We also looked at the bias. I also thought about presenting the MRE here. Basically, we see the same tendency. So also when we calculate the skill score with the MRE, then we are around 1 or 2 percentage points lower than for the skill score of the RMSE. But it is exactly the same tendency. Yeah.
Okay. Thank you.
I mean, I have the slide here. I have it as a backup slide, but yeah. I just.
Oh, you did. Okay.
I didn't want it to have, I thought it would be too crowded, the plot. That's why I took it out.
Okay. That's fine. Thanks. I'm sure that can be made available afterwards. Here's a general question for everybody. How do you see ASI forecasting in a tropical climate? Do you think it will be more difficult to use ASI forecasting in a tropical climate?
Yes.
Would you like to take that on?
I suppose it will be more difficult. Yes, I certainly for our physical model it would be more difficult, as if you have a more turbid atmosphere, then the cloud detection will have a higher uncertainty. I'm not sure about the deep learning models. So maybe you can, if you have a sufficiently large data set, then maybe they can overcome this. But certainly for the physical model, at least for this processing step of cloud detection, and also if you want to include a cloud classification, then it will be more difficult, especially if you have high layer clouds. So we see this problem already under really turbid conditions at PSA, or also in other locations where we have the system. So yeah, it's more difficult, certainly.
Yeah, if I may add on this,
sure.
Yeah, it's difficult. However, across the globe, the all images will have the best results when you have some nice puffy cumulus clouds with discrete edges. When you have other type of clouds like cirrus or very mixed type of clouds, then yes, there is a challenge there.
Yes, I would understand that. Anybody else on the panel would like to make a comment about that? Yeah, the tropical cloud structure is very complicated compared to other regions. So now this question is one that, of course, I also had alluded to in the past, and I would really like to hear the views of the panelists on the interest that the solar industry itself has in using these ASI systems. Which speaker would like to address that or start addressing that? The role of utilities and the use of these systems by utilities. I know there's some examples around the world where they are using them. I don't have at my fingertips any near-term results of their success in these systems, but can any of you address that question? Maybe I'll start with Jan, since you're the lead of the task.
I don't have too much experience regarding this. It is used for CSP plants to enhance the running of them. It is interesting for a combination of diesel PV hybrid plants. In this case, the diesels can be shut off if they foresee no clouds coming in the next 10 minutes, for example. These are the examples I know just by now, but I guess DLR and also other partners have more experience regarding this.
Well, from our side, we can say, but this is modeling, so it's not already applied. So what we try to analyze is whether or not the nowcasting system has a benefit for a larger PV utility plant with battery storage under a grid code where you have ramp rate restrictions. And at least from our modeling results, we could show that under such conditions, despite the uncertainties of the nowcasting system, it can be of a benefit if you preemptively partially curtail rather than using the battery storage, because you can reduce the overall capacity of the battery, and you can also reduce the discharge and charge cycles needed by the battery. And our first economics studies showed that there is an economic benefit under such conditions, but yeah, these are modeling results, so it's not yet applied.
Yes, for sure. The ramps have a significant cost implication to utility operations. Yeah, go ahead, Andreas.
Yeah, if I may add on the comments from Jan and Jan, there are also potential applications and some very good works on all-sky images networks, and this is very highly related to also to urban applications. We have initiatives like climate neutral cities. We have the solar cadasters, and we need the shadowing over the cities, and this could be done by all-sky images. There are numerous potential applications, even with buildings with electrochromic windows that don't have a very good time response in changes of the sunlight. So you need to have some forecasting system in order to change the properties and not leave the inside dark or maybe too bright when you have changing conditions in solar irradiance.
Okay, thank you. Let me move on to the next question. There are two questions together here. I'll try to combine them. The question is about what data you use to train your model based on DL/MI, and are all the camera, or is the same algorithm applied to all the cameras? Or are they all treated the same way? So again, I'm not sure who that question was addressed to, but sounds like one need to Stavros.
I think that, yes.
Oh, go ahead, Stavros.
Okay, yeah. All the cameras were set up and did in parallel observations, but there are 4 different hardware systems. Those 5 different hardware systems, on them applied the 5 different nowcasting systems. There are 5 different individual systems that provide the solar irradiance nowcast, but only ASI 1 and 2 rely on the same systems with only one difference, which is the cloud segmentation algorithm that they use. But from the 3-month observation campaigns, the days were divided based on the total, the percentage of the total cloud types. For example, we had 6 different cloud cluster days that all the days were classified, and we choose a great amount of days in order to train the algorithms. In order, for example, if we have 50% of, we chose 50% of the days to train, for example, for cloud-free days, and the rest, 50% of the days they are selected in order to do the validation.
Okay, thank you.
David, this was a discussion also within the group of the participants, how if it will be possible to use different softwares on different hardwares, not only the mother camera hardware. However, at that point, it was clear that we needed too much time. I mean, and a lot of retraining of some algorithms. So every group came with his own hardware and the accompanying software.
Okay. Thanks for that clarification. Yeah. Bijan, I know earlier you had your camera on. Didn't know if you had further comments on that question. Otherwise, the next question is addressed to you anyway. This is to Bijan. Again, thanking you for your presentation. Do you use stereo vision in your analysis? And if not, how do you deal with, or have you any clue about vertical distribution of clouds?
Yeah. So we do the stereophotography. So we try to identify the cloud height of every single cloud. The problem is we have little information about the vertical thickness of these clouds itself. So we have some approximations, and under certain cases, if the cloud is in a certain position where with the right angle, then we can also measure the vertical cloud thickness. But basically what we do get is something like the cloud center height, the average height of the cloud. That's what we can identify. And we can also, under conditions with multi-layers, if the layers are not at the moment like really overlaying each other from the point of view of the clouds, we can also identify clouds with different cloud heights. But at the moment when they start to overlay too much, then it is going to be really difficult. And then we will identify the cloud height of the dominant layer, which is quite often the low layer clouds, so cumulus clouds or stratus clouds.
Okay, thank you. These next questions are also addressed to you. I think it's two different questions. I'll read them both. The first one is, did you compare the proposed model with RNN, LSTM, etc.? I personally don't know what those algorithms stand for.
We also looked at LSTM, and as I said, so LSTM and the transformer models both are quite suitable for the sequential data. But this is also what is shown now in the current literature, is that these transformer models, which are more recent than the LSTMs, are outperforming them quite often. And this was also our experience. So we did benchmark it internally, and the LSTM model was also quite performant, but the transformer models were better. And yeah, that's why we chose them. Okay.
And then the same person asked, which software or tool did you use for training the deep learning models, such as TensorFlow, PyTorch, etc.?
PyTorch.
PyTorch. Okay. Very good. I believe. Let me see if anything more has come in. I don't see any more questions coming in. So we have just a few minutes left anyway in the webinar, but I could either turn this back over to Arabella, or unless first, if any of the speakers would like to make any final closing comments about this work and the future prospects. Is there any further last message you'd like to give our participants?
Not more from my side. I mean, I told everything.
Good.
So
and
we're looking forward for the new outcomes and innovation from all images.
Very good. It definitely is interesting research, and I know it's ongoing, and so there will be further results probably to report maybe in another year or so. Jan also highlighted some of the key deliverables coming out of Task 16 over the next year or two. So stay tuned. I think we'll see more of this work being presented in the future. Jan, did you have any closing comments?
No, thank you. No, from my side, everything's okay. Yes, thank you very much for the presentations and for you for the moderation.
Okay, well, thanks, Jan, and thanks to all of our panelists for their very good presentations on this interesting, fascinating topic. So what I will do now is turn the microphone back over to Arabella for any closing comments she might have, and I'll sign off, and thanks again.
All right. Thank you, Dave, and thank you to all the panelists and of course you, the audience, for joining us today. This has been the final webinar with ISIS for 2022, but fear not, we will be back in 2023. As Dave mentioned, I'm gonna have a few more closing remarks and then we close for today. First off is the recording and the presentations will both be available on the ISIS homepage in a few days. So the webinar has been recorded and the speakers kindly sent in their presentations for you. So just give it a few days and then we can share them with you online. And to our ISIS members who might be on the call and to everybody who might be interested in joining ISIS as a member, as an ISIS member, you have unlimited access to all past webinars ISIS has ever done in its 10-year history of doing webinars. And those are accessible to you via the ISIS webinar archive, and you can just log in to your account and visit the archive that way. And then another benefit we share with our members is the possibility to obtain a certificate of attendance for the webinars. So if you are an ISIS member and you are interested in getting that certificate, just send me a quick email and send it to public.relations@isis.org to get your certificate. And then finally, thank you obviously again for joining the webinar. If you want to stay in touch, again, please send us a message to public.relations@isis.org. We always look forward to your feedback or your comments on the webinars or wishes for future webinars. And we also have a little survey coming your way. It's going to get launched right after the end of the webinar. And by completing the survey, you do help us a lot in providing even better services on these webinars for you. And with that, I'm happy to close for today. Thank you again to everybody who attended and who joined, the speakers for taking the time to come and present for us, and to the moderator and the entire team. So to all of you, have a good day and see you again in 2023. Goodbye.